and welcome Avid Learning and our partners, the Consulate General of the United States, Mumbai, welcome you to an enchanting evening that is as much about mathematics as it is about poetry, theatre, and being human. Today, novelist, mathematician, and playwright Manil Suri will be in conversation with journalist, author, and Maths Aficionado Dilip D'Souza as they discuss the writing of Manil's most recent play, The Mathematics of Being Human, a provocative classroom drama that explores the nexus between mathematics and the humanities. The discussion will be preceded by an enactment of 2 episodes from the play by Manil and theatre artist Dilnaz Irani. A brief introduction to each of our speakers. Manil Suri was born in Mumbai and is a professor of mathematics and affiliate professor of Asian Studies at the University of Maryland, Baltimore County. He is the author of the novels The Death of Vishnu, The Age of Shiva, and The City of Devi. His fiction has won several awards and honors and has been translated into 27 languages. He was named by Time magazine as a person to watch in 2000. In addition to his writing, he is involved in several mathematics outreach projects as this play. Dilip D'Souza is an award-winning writer and journalist who writes about themes like development, nationalism, science, poverty, as well as travel and mathematics. His writing is fueled by travel, for he believes he must know and understand firsthand the issues he writes about. He has won several awards for his writing, including the Statesman Rural Reporting Award, the Outlook Picador Non-Fiction Prize, and the Newsweek Daily Beast South Asian Commentary Prize. He has published 4 books, a monograph of essays on patriotism, and has also contributed to a number of anthologies. His most recent book is Final Test Exit Sachin Tendulkar. Dilnaz Irani is a theatre and film actor and has acted in plays like Vagina Monologues, Black with Equal, Project Strip, Antigone, and Haya Vardhana. In film, she was in Ashutosh Govarika's Jodha Akbar, 68 Pages, Heroine, and soon to be released Arigat by Hansal Mehta. Before we begin the evening, we also have a very special preview for you. On behalf of Teamworks and the Jaipur Lit Fest team, we are pleased to unveil here in Mumbai the trailer to the 2016 edition of the festival. Avid has been collaborating with the Jaipur Lit Fest since 2013, hosting their curtain raisers in Mumbai and presenting panel discussions featuring artists and thinkers such as Salima Hashmi, Kamila Shamshi, Mark Kinn, William Kentridge, and Glenn Lowry. This year too, we will be presenting a very special panel titled A Week in Hell, The Narrative Art of Molly Crabapple, in conversation with William Dalrymple, which will feature the works, arts, and activism of Molly and her incredible journey through war-torn Syria, Guantanamo Bay, and Abu Dhabi, amongst others. Another event we look forward to at the festival will be with celebrated Magnum photographer Steve McCurry, famous for shooting the stunning Afghan Girl for National Geographic, presented by our collaborators Rolly Books. Steve will be launching his new book titled India with 140 extraordinary panoramas of our country and its people at the festival, post which Avid, along with Rolly Books, will be presenting the Mumbai launch of his book in this very room on the 25th of Jan. Please stay tuned for more details. For those of you in the audiences who will be attending the Jaipur Literature Festival, please inform us at the registration desk to get a chance to win free invites to special events at JLF, and you will be informed via email. We will now play a short trailer to the magic that awaits us at JLF 2016.
my name is Anamika Chakravorty. I'm the Cultural Affairs Officer at the U.S. Consulate General in Mumbai. So that means that I run our library at the consulate, I run a robust visiting speakers program, and we do a number of thematic programs as well. So we very much appreciate our partnership with Avid Learning. A special thanks to Assad and to his team for doing a wonderful job of getting all of you out here on a Friday evening. We really appreciate your time here. I'd love to get a sense for the audience, so let me know how many of you are here for the mathematics part and how many for the being human part. Mathematics, let me hear it. Okay, and the poetry, the literature, the being human part? And who's got a foot in both worlds? You're interested in the intersection. Fantastic. Well, I know that you are in for a really good evening. Do we have any alumni of U.S. universities here? A few of you. Always happy to see you here. So those of you that have gone to U.S. universities will know this, but let me do a little bit of scene setting for those of you who haven't. The co-authors of this piece, Michelle Osharau and Manil Suri, were inspired by an actual class that they taught together on mathematics and literature, but the play is highly fictionalized. It amplifies the tensions between the two disciplines. So, for example, in the play, the characters are forced by their university to co-teach this class if they want to keep their jobs. And in reality, as far as we know, there's no requirement at any university that professors do this. They do normally do it voluntarily, as much as professors can be said to. So I hope that you will enjoy the evening. Manil has also asked me to remind all of you that while we do have a theater representative in our midst who will be doing the reading with him, he himself is a professor and a writer and not an actor. So please be generous, be patient, and enjoy the evening. Thanks so much.
Looking for, are you Michael Pearson? Professor Pearson?
Yes.
Good. I was a little, I've never been inside this building. I'm Naomi Kessler. From English?
English?
Yes, I emailed you about the ID requirement.
ID requirement?
Interdisciplinary. You know the thing from admin about tenured faculty? Being required to teach with someone from a different department? To keep their tenure, you should have gotten a notice. The registrar or maybe a computer matched us up.
Oh, yes, of course. Come in, Dr. Kessler. Please, call me Mike.
Naomi.
Yes, I did get that notice. I had every intention of responding, of telling them that they'd made a mistake. I mean, the requirement is ridiculous enough. All these crazy seminars and couplings they keep putting us through. But English and mathematics? What were those geniuses thinking? But I meant to send in an objection, but I never did. And good God, you didn't either? So is this it? Are we stuck with each other?
Okay, I didn't try to get out of it. I thought, I mean, the students have to take their general education requirements, so...
So why not inflict some general teaching requirements on the faculty? Yes, I've heard all the arguments.
Besides, I'm not afraid of math.
All those deans and vice presidents going on about interdisciplinarity, like crows at the sight of carrion. At least finally they've put their money where their beaks are. Lucky us.
I can do maths.
A complete waste of time, dragging mathematics into this mess. All the research I do, but who cares about theorems anymore? A year ago, I couldn't even spell interdisciplinary, and now I is one.
Excuse me?
It's an old engineer joke. I used to be an engineering major.
Me too.
Oh, really?
No, I'm kidding.
Oh.
Okay, so why don't you go ahead and submit that petition?
Oh, look,
I'll request a new co-instructor, maybe someone with the knowledge of basic English grammar, and we'll see where we can...
I didn't mean to offend.
I am not offended. To tell you the truth, Mike, team teaching with a mathematician falls on my wish list somewhere under chewing glass. Like, let's just be clear that I am not the one backing out of this. I am not afraid of you people and your whiteboards and your Greek. Write that in your little petition.
You people? What's that supposed to mean?
Yes, I should have expected it. This hostile view of the humanities.
Hang on.
How you mathematicians think what we do is a complete waste of time.
You're taking it the wrong way.
Well, sure. I lack skills in deductive reasoning and critical thinking. We don't do much of that in the humanities, right?
No, that's not what I meant at all. I like music. I go to the theater.
That's art, not humanities.
Books. I like books. I've even written a few children's stories with mathematical twists to them.
Are you serious?
Keep that under wraps, would you?
Yes, I will.
I haven't really shown them to too many people. Hey, maybe you have suggestions where I can send them for publication? I really have a lot of them, you know. Look, I didn't mean to.
No, really?
Really.
Okay, so what do we do about this seminar? Because I'll have to let my chair know.
Okay, well, let's do it. Why not? Yes. Show the world how open-minded we mathematicians are.
Good one. So, the mathematics of being human.
What do you think for the course title? Do you like it?
I do. I like it. But what does it mean exactly?
Oh, I thought mathematics, the humanities, their intersection.
Which you understand to be?
You hate the title, don't you? I can tell. We can change it.
No, the title's good, Mike. It's what we're going to teach that I don't quite get.
Oh, I was coming to that. It's quite amazing how it fits in. This paper I've been studying. How the differential equations used to track epidemics can be reformulated to model the spread of ideas. Quite thrilling. Surely that's humanities-ish, right? The spread of ideas like a disease.
Differential equations.
They're only first order.
Yeah, I assume that. You do realize the seminar has been given a humanities listing, right? It's a HUM course for freshmen who've received scholarships in the humanities.
Yes, I saw that, but some of them would have had calculus already, right?
Maybe, but not all.
We might need to brush up on a few things, of course. Little time on derivatives, just a smidgen on limits. A week. I bet I could have the class up to speed in a week.
No, whoa, time out. Again, this isn't a math course. The purpose is to connect mathematical ideas to humanities subjects. We need to discuss things.
But how can you discuss anything when you don't know the
things
math?
that have a mathematical something to them. I thought Alice in Wonderland to start.
Oh no, not that chestnut.
Why not? Lewis Carroll was a mathematician.
Just because the story is written by a mathematician, people turn themselves inside out to see all sorts of mathematical effects in it.
There's books written about the math in Alice in
True, but you really need to know higher math to appreciate what he was saying, not something the students would understand. Nor you, I'm guessing.
Nice.
I'm sorry, really. But we can't do Alice. I've never actually liked that little brat. And I've thought about children's books and math. Remember I told you I write children's stories? Hey, maybe we can use one of my books.
No, you're right. Children's literature may set the wrong tone.
Well, I suppose there could be better choices.
Yeah.
Fine. I see you've thought of your list. I've thought of mine. Let's just fire away.
I thought that's what I was doing.
Well, do better.
Will do. And it's your turn.
Well, surely you must have come across my top choice in the library. A book that relates the history of math, but frames it in terms of the solution of the most famous mathematical theorem that's ever existed. You may have heard the name Fermat, who wrote in the margin of his notebook...
Title, please.
Oh, okay. Fermat's Enigma by Simon Singh. They call it Fermat's last theorem in India.
Didn't read it. But a book with theorem in the title...
Hey, you can't just honk Fermat away.
I am avenging Alice. And now, something you'll wish you'd thought of first. Gödel Escherbach.
To dance.
Oh, please, you're just bitter about Fermat.
Would take ages to understand all the math.
I read it as an undergraduate. I did.
You've been honked, Naomi. My turn. Logic comics, an epic search for truth.
The comic book. That one I saw. All those miserable logicians going nuts, depressing.
Wait, let me try again. Flatland. All right, knock it off.
A beautiful mind. At least let me finish the title.
From Euclid to...
Goodwill. Okay, stop. I have a play that's perfect. Don't you dare. Arcadia by Tom. No, really, this is... I'm going to take that away from you in a minute.
The curious incident of the dog in the nighttime. Did you hear me? I said the curious incident of the dog in the nighttime.
I heard you.
But you didn't honk.
The book by Haddon about the boy with Asperger's who deals with the world through math. It's on my list too.
You mean we actually have a text?
We do.
Hooray! We did it! We have a text!
We did, but that's only the first. We need at least half a dozen more for a humanities seminar. Brace yourself. I want to do King Lear.
Ah, Shakespeare. Mm-hmm. Why don't I take another look at Alice?
Thank you.
Thank you.
So that was a lot of fun, Manil. I enjoyed that. I've read the play, so I had some idea of what is coming. But seeing it enacted, of course, is entirely different. I love the horns.
Thank you.
Round of applause again for the play, guys. That was fun. I'm told it's going to be enacted in full in Delhi in a few days, right? Next week.
Yeah, by Atelier Productions, Kuljit Singh. He's doing it at the American Center.
So if any of you are in Delhi, please go take a look.
It's on the 14th and 15th.
Yes, okay. All right, so are we showing something first?
No.
So that's later, okay.
Yeah,
all right. Okay, so we've seen a bit of your play, and I'd like to take off a little bit from that, Manil. Some of what the play is about, it reminded me of when I used to be in software, when I was a programmer, a mere programmer, but we had a healthy contempt for the guys we call suits, the people who did marketing, and I know that the contempt was felt both ways. So, and I learned that later because we thought we were superior, of course, the guys doing the programming. But so I mean, this is in a sense something like that. There is this contempt that the characters in your play feel for each other and scorn for each other, and then that in the end it develops into something else. So I just wanted to start by saying, is this latent hostility? Is it between the disciplines? Is it first of all, is it from personal experience that you feel this, and why does it happen, you think? Can you just give us some thoughts on that?
Yeah, so let me tell you how the play came about. Michelle Oshiro, who's a professor in English at my university, she and we had collaborated. She's also a dramaturg. She works with the Folger Shakespeare Theatre. So we had collaborated on this play called Arcadia. Has anyone seen that? It's got a lot of math in it. And so later on, she said, why don't we teach a class together? And that was, this thing that you saw is very fictionalized. It's really exaggerated and so on. But we had some of the same tensions in there. And throughout the course, we would exchange 100 emails every weekend trying to figure out, she would always say poetry, King Lear, this, that. And I would be trying to put in calculus and this and that. And the students were just caught in the middle. So what we decided was, after we finished that, we wrote some articles on it. And then someone saw it in Canada and invited us to give a talk about it. And then since I knew that she had this theater connection, I said, well, let's just write a play. And we'll surprise them. And we'll just do a reading there. And then she said, what if we don't finish? We said we won't really tell them. And so we actually wrote this play. And about a week before we went there, we announced that we are going to do a reading and we need 2 other actors. And they were very sporting, and we actually went ahead and read it. And it went very well. But I think the play actually just picks up on those things and just, amps it up several degrees. So I have to explain that we weren't actually fighting each other, like in the play, even though it feels that way. So why does that happen? Well, there's always been, this is something that has been true since, what was that famous essay, The Two Cultures, by C.P. Snow, yeah. And he brought this up way back in, I forget if it was the 30s or 40s, yeah. Saying that, there are these two cultures, and one is the science and math side, and the other side is humanities, writing, literature, and so on. And they kind of have their own spheres of influence. They kind of don't really talk to each other as much as they should. And they don't really understand each other. The vocabulary is different. And so there's been this kind of tension that's been historically true.
Okay.
I think now this whole idea of interdisciplinary stuff, I think they're really trying to break that down. And so there are several offshoots that people are trying to do to bring these two together. Because really, we all do both mathematics and literature. Even if you hate mathematics, you do it. Even if you hate literature, you probably enjoy parts of it.
Yeah, I want to come to some of that a little later, but a little bit more about the play. You've partly answered this, but despite the tension that there is in the play, by the end of it, there is clearly the professors are affected by each other and by what the other person is saying. I mean, there is a moment of real enmity and hostility, but they come back and there is some. So did that also happen to you in your experience? Does that also happen that there's this understanding that develops over time of each other? Yeah.
I mean, if you really talk to someone, and it takes when I say talk, I really mean listen. That's the key. Like I really was against this King Lear. I mean, it's a math thing. Why are you putting King Lear into it? It still doesn't make complete sense to me. But anyway, we did King Lear, and she insisted because she's a Shakespearean scholar. And what we found was that by looking at it together, we could actually find connections with mathematics in King Lear. Like, I don't know if people know the story of King Lear. That basically it starts with this king who decides that he's going to divide his kingdom up between these 3 daughters. And one of the things that happens is that one of the daughters says, I mean, it's a complicated story, so I won't get into this, but one of the things that if you look at the play, the word zero, the word nothing is repeated something like 42 times in the play. So we started looking at that, and we found some literature on that. It turned out that the number 0 had just started being known in Europe. People had started using the number 0. And so I think Shakespeare was, and other scholars think that Shakespeare was actually influenced by that. So we tracked that in the play. There's a famous thing, and that's mentioned in the play too, about something like if you have an angle, and you just have a compass and a straight edge, can you divide an angle up into 3 pieces? Just like trisecting it, just like King Lear was doing it for his kingdom amongst 3 daughters. Can you take an angle and divide it? So we put that, I gave that as a homework problem to students. And then later on, I told them after they had struggled for a week that it's actually mathematically impossible to do. So there are these connections, and you can really find how it's a holistic thing. Like, all of these elements are elements of living and of life. And so you have to kind of find the mathematics in that. And I have to admit that Michelle was much more amenable to it than I was. And that's sort of reflected in the play, yeah.
So taking off from that, though, is that a reflection on you, or is that a reflection on mathematicians in general?
I think, if anything, I should be more open-minded since I am, in the literary world too.
Yeah.
I would say mathematicians in general have a long way to go.
Okay.
I mean, in terms of being receptive.
What about programmers and marketers?
Well, I don't even talk to them.
Okay. All right. Okay. Okay, so then let's step back a bit, Manil, and ask the wider question. I think your play raises is why do so many people have a fear of maths? And many people will say, they almost with a hint of pride, they'll say, I just can't do mathematics. I don't relate to numbers. You never hear anyone saying the same. I just can't relate to letters, or they don't say that. And if they say it at all, it's not with pride. So why do they say that with numbers?
Well, although I will say that this play was actually at the American Maths Society, their annual meeting, okay. And certainly some mathematicians said, well, we don't see plays, so they didn't come. So there's a little bit of that both ways. But you're right. The real stereotype is people announcing that, okay, well, I can't do mathematics. I hate mathematics.
So why do they say that?
And there's several reasons, I think. First of all, there's the whole issue of how mathematics is taught. And that's a real problem. And that's something that hasn't been solved yet. And I don't know when it will be solved. I mean, there are different approaches. And the hardest thing, I think, is that people react to different things. So there's no one way to teach mathematics. Yeah. Like some people love memorizing tables and being able to do calculations and so on. Some other people like to do puzzles, so they might be really drawn in by the puzzle forming, puzzle solution kind of aspect. And then some other people want to see applications. Some other people like abstractions. So there's a whole bunch of things. And unfortunately, the educational system, whether it's here or it's in the US, it's always geared to one size fits all. Let's have one framework and let's just stuff everyone inside. And the second thing is poor training. Like mathematicians are not necessarily good teachers. Often in schools, you have one teacher, like even in the US, you'll have a gym teacher who's teaching mathematics at the 5th grade. And some of these teachers themselves have had problems with mathematics.
Yeah. So they're just passing on those problems.
Yeah, they're passing on the problem. Yeah. I mean, often children get it from their parents. Yeah. So, if any of you say that to your kids, then okay, they'll be prideful too, that they don't care about mathematics. Yeah. So, there are all these cycles that keep occurring, I think.
Do you think that, what's the price that a society pays, you think, for being enumerate in this sense? This is a word actually that this mathematician we were talking about, John Allen Paulos, wrote a book called Enumeracy, which is about people not being so familiar with numbers. So first of all, is there a value to being familiar with numbers, and what's the price that we pay for not being familiar with numbers?
So there's two things there. First of all, if you learn a lot of things in school, and most people probably won't ever need them. No, that's true. Okay, some of us go into calculus and become engineers and so on. But a lot of people in day-to-day life, you probably won't encounter a lot of the mathematics that you necessarily learn, like quadratic equations. Many people will probably never do them. But that's not what numeracy is about. No. Numeracy is really something else. It's being able to tell, being able to make mathematical arguments in your head, being able to weigh things, roughly speaking, and say, someone claims that, okay, inflation has risen by this much, and, this effect is ascribed to this, and percentages and so on. And, they make this smoke screen, and you can't penetrate it because you don't have the theory, you don't have the training, or you don't have the confidence to do that. So that's the part that's the most crucial to be able to penetrate as a society. And when we cannot do that, politicians and other special interest groups can say whatever they want. And they can, make all these arguments based on so-called mathematical truths, based on statistics, based on all sorts of things.
And nobody challenges them.
And you can't challenge them. So that's the unfortunate side. So numeracy is not necessarily the same as calculation. Like many people, they have a problem with calculation. They might not be good at, multiplying 27 by 9 or something. But that's not really needed. That's not really. It's really something else that we're after.
Actually, I think it's a mindset. For example, it just occurred to me. You're standing in the shower and having a hot water bath, and you turn on in India, we turn on the geyser for a long time, right, to make the water hot. And you find that if you haven't turned on the geyser for enough time, then you can't really control how hot the water gets or how cool the water gets, because that's a function of the difference between the temperature of the cold water and the hot water. I mean, I think this is a lesson that you all learn. But there is something intrinsically mathematical there, I think, and that's what I mean. I think, and when you look at it like that, I think most of us actually are numerate. It's just that we don't realize it. We're always making estimates. We're driving or you're walking along the road. You make an estimate of how fast that car is coming, and therefore can I cross the road? That's some kind of mathematical thinking that's going on. So why do we forget it at times when, for example, when we have to confront politicians for what they say?
Well, it's a little harder than that, I think, just because, I agree, we all have this innate mathematical ability. In fact, there's Keith Devlin.
Yeah.
There's a person who's written several books on this, how, they've done experiments with babies, for instance, newborns, and babies can tell the difference between 1 and 2 and 3. Even birds, supposedly, they're able to count till about 3 or 4. So it's like 1, 2, 3, 4, and then many. That kind of thing. So they've been able to show that, like, intrinsically, many life forms have this mathematics that's built in. Now, that's not enough to penetrate statistics, for instance. You need a lot more. You need some training. Maybe that's the hard thing, because mathematics isn't easy either. So, like, almost anything, if you set your mind to it, you'll probably be able to penetrate it. But not everyone wants to do that. Not everyone is motivated. Not everyone has the encouragement. So again, there's a bunch of things. You can't just say, okay, we are all naturally mathematicians and let's hope for the best. You do need training too.
Sorry if I go on with this, but do you think all of us need that training to be a numerate society? And to what kind of level? Are we talking about high school level? Are we talking about just a middle school or college? What do you think, what's the kind of mathematical training that all of us need to be a minimally numerate society?
Some of the things that people have been suggesting is more emphasis on statistics, for instance, than calculus, perhaps. So that's a thing. The other thing is tying it more to actual examples. Like often people have these word problems that you've been through calculus. So, a tank is being filled at 7 cubic millimeters per second, and what is the rate at which the height is changing? Those kinds of things are less interesting. Yeah. It's hard to make problems that are really relevant and that come from society, and then make them to such an extent that people can actually see where the mathematics is playing. So that's the hard thing, and that's what needs to be done. So some of the books that I was mentioning, Keith Devlin and so on, what's his name? John Paul.
John Allen Paulos.
Yes. I mean, some of his book, Numeracy, he really does that. He says, and then he has another one, right? A mathematician
reading the
reads the newspaper. He really shows how these mathematical ideas come up. So maybe that could be done in a more formal way, in a class.
Okay. Going on from there, I wanted to talk about something else that your play got me thinking about because of different mentions all through. Is this idea of beauty in math, and this is also, again, getting to some of what we have been tasked to speak about today, about poetry and beauty in mathematics. So a lot of people don't find it easy to believe that you can talk about beauty in mathematics, and I think as a dabbler in the subject myself, I find reasons to find things. I find things that are beautiful. I just want to rattle off 1 or 2 or 3 for you. For example, there are models of how birds fly. And it shows you that with a few very simple rules, you can model how a flock of birds comes together. And if you see flocks of birds flying around, it's a really beautiful sight. And to know that there are these really simple rules that form that, I think that is really wondrous. Another example, we've all heard of you mentioned in your play pi, which has it's what we call an irrational number, and what that means is it has an endless expansion of decimal digits. and they never repeat, and there are no patterns. But what the meaning of that is that somewhere in the middle of pi, in somewhere I can find my phone number or your social security number, or if we took this lecture and somehow managed to encode it into numbers, we would find that long expansion of numbers, probably find it somewhere in pi. And
Probably. That I'll just contest a little because that's not been proven.
No, it's not been proven.
Right? But people, they've done statistical tests.
But my number is in there.
Okay, so that's good. But they've done statistical tests that say that just about all information should be in such numbers.
Yeah.
But they haven't been able to prove it. So that's still an open, but they might be able to. They suspect it's true.
But that itself, I find, the fact that is so unknown, and that in a sense, all our knowledge could be in that one number in one
amazing.
sense.
Right.
That just is amazing to me. So things like that, and just one more example. So there are these little insects called cicadas, which I'm sure you've run across in your part of the world, which there's a particular species of cicadas, I don't know if it's cicadas or cicadas, so excuse me, whatever it is, which come up, they live underground, but they come up once in 17 years. And it's called Magicicada septendecim, which means 17. And so the reason, there is one theory for why they come up every 17 years, and that has to do with the fact that 17 is prime. It's a prime number, and it's these cicadas have evolved to the point where they try to evade natural predators, and the prime number makes it easier for them to evade it. So you can look into the mathematics, but again, that's something that I find truly wondrous, that you can find out of something as natural as evolution, this little mathematical idea coming up. So these are the things that I find beauty in, and I just wanted to run them by you and ask you to react, and also to tell us a little bit about what you find beautiful in mathematics.
Well, I think those are all good examples, and one of the things that I like to talk about is the fact that, if you look at, this is my favorite. So first of all, I should just say, beauty in mathematics is a little different from visual beauty necessarily. There is more like intellectual beauty. You can see this idea, and it's almost like meditation sometimes. Yeah. A nice mathematical meditation is to look at something like a square, and then add another side to it, and you get a pentagon, and then add another side, and you get an hexagon, and then keep adding sides. You'll get a septagon, and then 12 sides, 20 sides, 100 sides.
What do you get at the end?
What do you get in the end? And if you think about it,
somebody said something. A circle.
Yeah, you'll actually end up with a circle. And now that you'll never actually get the circle because you can't add an infinite number of sides, but it's telling you that the limit of this is a circle. And that's a very interesting thing, that you start with a sharp, cornered object, and then you end up with the most perfectly symmetrical object that there is. So, it's ideas like that. When you think about it, you say, wow, that's neat. So that's the kind of thing that hopefully kids can be also made to realize that there is this beauty in this idea and other ideas.
When do you get I'm trying to draw this out of you. When do you get the circle? So let's talk about that. Where are we going to when we finally get the circle?
Well, this is, you're trying to get me to say something about calculus and scare everyone.
No, I'm trying to get you to use that word infinity. Tell us a little bit about it.
So that's the nice thing. A lot of these things, they involve the infinite. So you get a circle as the limit. You call the number of sides. If you look at the number of sides has to tend to infinity. It has to get closer and closer to infinity. As that happens, the polygon that you have gets closer and closer to a circle. I actually have a little thing, since we said about videos, but I'm going to actually go ahead and show this. Okay, because I have a little video, and I wasn't going to show this one, but let's see if I can pull it up.
Are we still projecting?
I want to go into something, because I don't think I don't know if what happened to the thing. No. Okay, wait. Let me. Where is the computer? I'm sorry. I know this is, but you just brought this up. I didn't know this was happening, so now
I put you on the spot.
Yeah. Why is it not? Yeah.
Does everybody here have a good idea of infinity? What does it mean? Or
So there's some sound to it. Okay, so this video, what I'm trying to put this in images, and it's going to show two things. It's going to show the circle, and it's also going to show the fact that if you start with a number and you take its reciprocal, 1 over x, if you start with 1/10, that's 0.1. Make it 100, it's 0.01. 1 over 1,000 is 0.0001. And so what's happening is that if you keep doing this, what you'll end up with is finally 0. So these two things are going to happen together if this works. If it doesn't, I'm just going to sit down and pretend I never wasted all this time. Let's see. Oops, can't open this file. Okay, let's see if that works. Okay, let's turn off some lights. My little show and tell.
Actually, the idea of infinity I find is so fascinating because of things like this, because of the different ways it comes up, but especially I found when I started reading a little bit more about infinity that this mathematician called Cantor, who found that actually there are different kinds of infinities.
Right.
And there are some infinities which are, in a sense, more infinite than others. And what was really nice about it was a demonstration how Cantor was able to show us that. So can I run that by you and ask you to tell us a little bit about that? Not so much about Cantor, but tell us a little bit about what these different infinities are. And can you put it in language that we would understand?
So you want me to summarize Cantor's life work in 10 seconds?
In
right?
a few seconds.
to an audience that hasn't heard these things before.
Yes.
Okay. Well, actually, if anyone wants a longer version, I have a video on YouTube called Taming Infinity, so you can look that up. Okay. But that explains all this in much longer time. But the basic idea is this, that what Cantor did was he really studied how do you count? Like when you learn to count, what do? What you're doing is you're matching things. So let's say you didn't have any numbers. You could still tell that you had the same number of fingers in each hand just by counting 1, 2, 3, 4, 5. You don't have to count. You would just be able to match these and say there's a 1-to-1 matching between these. So Cantor started doing this not just for finite sets, but for infinite sets. And he said, okay, I'm going to define the first type of infinity as any set that can be matched with a set of whole numbers. 1, 2, 3, 4, all the way up to infinity. We all know the whole numbers, right? 1, 2, 3, and that goes on indefinitely. So if you have a set of apples, let's say, and you could match, this is the first apple, this is the second apple, third apple, fourth apple, and you ran out of all these numbers at the same time that you ran out of apples, then you would be able to say that you had as many numbers as you had apples. And you would be able to say that this set of apples is infinite in this first sense. So that's what Cantor started doing. And he said, okay, let me try different numbers. So the nice example of Cantor is, let's say you look at the set where you don't just have 1, 2, 3, 4, 5, 6, but you start at the number 0. What happens then? Is that a bigger set? Do you have a higher infinity? Because now you have an extra 0. And the answer to that is that you still have the same infinity, because all you do is you match the 0 with the 1, you match the 1 with the 2 with the 3, and so on. And so you would again end up with the same number of infinities. There's a nice example of this, which is the Hilbert Hotel. Yeah. And this is the example where there's a hotel which has an infinite number of floors. Each floor has exactly one room in it. And what you do is you have a team or you have a bunch of people who come in, and it's an infinite number, and the whole hotel gets filled. Think of the numbers 1. The number first person is in the first floor, second person is in the second floor, and all that. So the whole hotel is full. And now one more person comes. Where are you going to put this person? You can't tell the person go up to the top because he'll die. You can't climb an infinite number of steps. So you can't say that. So what you do is you tell each person to move up 1 floor. And then there'll be a floor left at the bottom, so you can put this 0th person in. So that's what Cantor did. And then he started looking at other sets of numbers, and he finally came up with a set of numbers, which is the set of all real numbers, which includes pi and so on, irrational numbers. And he found that you cannot do this matching. So that meant that this set was actually of a higher infinity than this set, because there were things left over. You filled all this and there was still stuff left over. So this was a higher infinity. So that was the true genius of Cantor. I should just point out, though, that there's another kind of unfortunate stereotype that mathematicians go mad. And if you look at movies like Beautiful Mind, Proof, this, that, they're all going mad. And actually, I have to say this, Anamika, it wasn't you, but like some time ago, this was many years back, I told, I was going to give a math talk. This is when you were still in Churchgate. And I said that, I'm going to talk about this. And the person there said, well, can you make it something that people will understand? And so I gave a list of things. And the response I got was, could you tell people about the role of insanity in your own life? And I wrote back, I haven't gone mad yet. So
but did she mean insanity or infinity? Maybe she...
Insanity. So anyway, so that's what Cantor did. And Cantor, unfortunately, did go a little crazy. He actually went and had to go to asylum almost, a mental institution for a while. Then he recovered, started working on infinity again went crazy, went back. This went on for a while. And then finally, he gave up mathematics. And his last few years were spent in literature. He started looking at the works of William Shakespeare and tried to prove that they were all written by this man named Francis Bacon.
Yeah.
So that was that. So literature and mathematics.
I think have an intersection there. Yeah.
Right.
Yeah. Okay. Good. The reason actually I mentioned infinity again is because I just find that again a really wondrous idea.
It's my favorite part. I think,
and it's so beautiful. And this Hilbert Hotel really captures it so well, and you can think about that Hilbert Hotel in many different ways. If it's just one person who comes, you can find them a room. If there are 2 people who come, there are 179 people who come, you can find them rooms. But if an infinite number of people come, you can still find them rooms, and that's what's interesting about infinity, So, okay. The other thing that your little video reminded me of is when you're talking about these polygons turning into a circle eventually. There's this notion of fractals, which again involves infinity in a sense. And the reason it reminded me of that is that you can actually make very easily a certain kind of fractal which have a provably infinite circumference, but they have a finite area. So I find that an interesting idea. Right. And can you tell us a little bit about that, about fractals in general?
Right. So this is I'll just give this is a part of a talk that I did at go through this whole thing, but I just want to show you this first thing. What is a fractal? So here is the rule. It's similar to what you were saying. Here is the rule. I'm going to take a copy of this square on the left side and draw 3 copies. I don't know if you can see this. I'm in the way.
See?
I'm going to reproduce 3 copies of the pattern on the left in the box on the right. So that's 3 copies, right? That makes sense? So now I'm going to think of this as the input and that as the output. Now I'm going to take that same output and use that as the input, draw 3 copies of that pattern in the square on the right. So what I mean is, draw 3 copies of that. So you see what I've done? I've just repeated that but 3 times. And then I take that as that output and use that as my input, and I draw that. Wow. And now the question is, what happens if I keep doing this an infinite number of times, like you said? So I take that as the output.
Does it always come with that sound?
No. That would be good, wouldn't it? Each time you drew it on a piece of paper, that's what happened. So there is what, this is actually taken from Wikipedia. So this is the same thing. It's Sierpinski's triangle. And the 2 things that are really interesting about this fractal are, first of all, if you were to zoom in, if you were thought of it as a net, and you said, I'm going to fling myself on this net and hope that it catches me, you would just keep going through, because it doesn't have any area in it. So there's no area that can be defined. It's just all holes, basically. So that's one thing. And the other thing is, if you blow it up, you get the same pattern again. So the part that says there's no area, this is more kind of weird, but it's actually not a 2-dimensional object, and it's not a 1-dimensional object either. It's somewhere in between. So anyway, let's just. But that's an example of a fractal.
Yeah. So what I like about that also is what I alluded to earlier. The idea of birds that. The flocking of birds that comes out of very simple rules. Fractals, these beautiful, complex patterns come out of really, really simple rules. Very simple rules. What he said, just copy that, basically copying that square 3 times, and that's what happens.
Let me see if I can. I just want to show you one other thing, which is, oops, what did I do? Just this one image. You've seen the Sierpinski triangle. This occurs in nature. Let me show you.
Yeah, in shells, right?
Yes, look at this.
I'm sure some of you have seen shells like that.
So you can really see that Sierpinski pattern appearing in the shell. And the reason for that is that for shells, the way it appears is that the cells in the shell, as the shell is being made, there are mathematical rules that turns things on and off. It secretes a certain pigment, then it stops, and this just happens automatically because of that mathematical rule. So this again shows that we are all wired mathematically. There are all these very simple rules that are creating this pattern. So.
The other place you can easily see fractals are, and if you look at the next cauliflower you buy, the patterns repeat, or a head of a sunflower, or and there are other patterns there too. In fact, Manil, that actually gets to another thing that more and more that I read about maths and mathematics, I often find that the fundamental thing that mathematicians seem to be doing is looking for patterns. Would you agree with that?
Yes, absolutely. Yeah. I think that's the key to most of mathematics, being able to understand patterns, first of all, find them, understand them, analyze them, generate them, and it's all about patterns in anything that you look at. That's the key thing. And that's how we learn, actually. You see a pattern, and you see it again, and you see it again, and then you start wondering, what is this? What is the analysis? Where did it come from? And you come up with rules that will actually explain it. So that's a big key aspect of mathematics.
So, but is it the brain is, right-hand brain is pattern?
Well, people often say right brain, left brain, but from what I understand, it's not as simple as that, and it's like, that's a kind of misconception.
Okay.
It's an oversimplification. Like, we all use both parts of our brain, and both sides of our brain actually do bits of each thing. So it's not just all restricted to one side.
In fact, I'm going to read out a little quote. Have you heard of this actress and mathematician, young woman called Danica McKellar?
Yes.
Okay,
yes.
She had this really lovely, about just what we're talking about. She says one of the most amazing things about mathematics is the people who do math aren't usually interested in application, because mathematics itself is a beautiful art form. It's structures and patterns, and that's what we love, and that's what we get off on. That's what Danica McKellar said. And I think that really applies to math. And that's why there is so much joy and beauty in mathematics.
You have to be careful, though, because a lot of this joy and beauty comes, from abstraction. And not everyone thinks the same way.
Yeah.
And that's one of the kind of things that mathematicians often have a problem with. Like who would not love this thing? Well, a lot of people might not. And one of the things that happens is that, and this goes back all the way to, I think it was Plato or not Plato, but whom am I thinking of? Anyway, it goes back to, prehistoric time.
Euclid?
Not Euclid. Who's the Greek geometer?
Archimedes, Aristotle.
Pythagoras. Maybe. But anyway, he had a sign who said, "Let no one ignorant of geometry enter." Euclid. Was it Euclid? Okay. But now, Plato. It was Plato, right? Yeah. So I was right first. But now notice okay. On the one hand, it's saying it's making this restriction, but on the other hand, it's kind of conceited, arrogant,
yeah.
right?
Okay.
It's very arrogant. It's keeping people out, and that's the thing that I think mathematicians have to get over. First of all,
no, I think it's a matter of mathematicians conveying to an audience like this.
That's not enough. I think we can say, yes, it's wonderful, yes, it's beautiful, but someone might be sitting in the audience and not really agreeing. And in fact, I'll tell you, that has happened. When I talk about infinity, the same stuff that you talked about, after that I had a kind of survey taken. This is at my university. And one of the things, which I know who wrote it was an English professor, actually. And she said, she wrote in the survey, "I can't believe that people waste their entire lives thinking
doing
of
this
such
stuff.
things."
Okay. Yeah.
So, and that's fine.
Yeah.
But that's the beauty of being human, that there are different things that turn people on. And to appreciate this, you need training. Just like for music, classical music, you need a lot of training. To appreciate a taste in wine, you need some training. So so it's perfectly fine not to expect everyone to kind of realize.
Absolutely.
That.
No, but the point I'm trying to make is that I think mathematicians have a responsibility, perhaps, to convey their passion
right.
to the general public, and whether that fires the imagination of other people, that's another matter. But I think I wish more mathematicians would do it and tell us about what are they passionate about,
right.
and that's why I'm trying to get you to say something about this. Okay, so I want to just ask one more question before we let our audience in on this. So. You chose Manil to leave India and to study and work in the U.S. Do you think you would have had the same exposure, experience, training, thinking that you have now had you stayed in India? And do you think that is what if you were starting your career today? Would it have been any different?
Well, it's very hard to say, of course. I know that over here, certainly I got my switch to mathematics here. So what happened was that I was in Jai Hind College. I used to like mathematics, but my mother, she actually gave me the worst advice I've ever heard, which was that she hated math. And she said, don't go into higher math. It becomes very difficult. So, something like that. So, but then, of course, she was very supportive and all that. And I didn't mean to say it that way. But anyway, I was a physics major. And I was, doing my BSc in Institute of Science. I was in Jai Hind first, then I switched to Institute of Science. And there was a professor there, Professor Huzur Bazar. I don't know if anyone has, yeah. He was our algebra teacher. And he would always, convey the passion. And he was really passionate about it. And he was a great teacher. And he's the one who slowly started working on me and said, "Why don't you switch to mathematics?" And little by little, I finally switched. after 1 year. So I had to do some of my exams again and so on. So I really got that encouragement from him. And that's, so, it's hard to tell what would have happened afterwards. Yeah. If I'd followed in, but he's the one who said, why don't you go abroad? So I just followed that. So it's like here, there's the Tata Institute of Fundamental Research, which has great facilities. And I think in India, the mathematics that's done is perhaps, at least when I was here, it was more well known for statistics and for pure mathematics.
In Indian mathematics,
yes.
you mean? Okay.
And I think
Has
recently,
that changed? Yeah.
recently they've been trying to increase the emphasis on applied mathematics,
Okay.
which somehow here is often thought of as more as theoretical physics. But the applied mathematics is,
Is that a function of funding, you think, or is it why is there that emphasis?
It's cultural too, I think. If you look at the most famous Indian mathematician, Ramanujan, he was doing number theory, which is very pure mathematics. So it's just got a strength in that. So I think that's where, when they're teachers, they'll teach their students the things that they have learned or that the research.
But you
that
mentioned
they do.
applied math. You mentioned
Right.
applied is what's happening more in India now.
No. I said they're trying to.
They're trying to
increase.
encourage that. Yeah, okay.
Because that's the kind of mathematics that is used a lot. So, but anyway, when I went, I was interested in pure mathematics, but I ended up in applied. So.
Okay, good. Would any of you like to ask Manil a few questions? Do we have a mic, or shall I just here? Let me.
See, long ago I attended a lecture on Vedic mathematics.
Okay.
Now, in what way is it different from the mathematics we understand? And I have also heard about Vedic astrology.
Okay, let's not combine those two.
No, okay. In a way, the word Vedic.
The reason is astrology is not a science.
No, it's not.
So let's make that clear.
But they're trying to make it
And
a
the reason
science,
for that
yes.
is that science usually is something that you can refute,
Yeah,
that you can
just
prove
one.
is incorrect. Whereas astrology, if you have somebody's Janam Patra or something, then it's not accurate, then you can always say, well, you didn't get the exact second that he was born or she was born. And then if you try to correct that again, you can say the same thing. So, but in terms of your question about Vedic mathematics, from what little I know, it's mathematical things that have appeared in the Vedas. And there are a lot of special rules that allow you to make calculations very quickly. And these kinds of rules have many years later been developed by people like Trachtenberg. You've heard of that system. But from what I've seen, a lot of it has to do with calculations that use some special rules. Like you can easily multiply 11 by any number by addition instead of multiplication and things like that. So that's one aspect that I'm familiar with.
Manil, I am from your time. I'll be 76 a couple of months. And I know Huzur Bazar, when he got the award, I was in the Department of Statistics.
Okay.
And it was a big thing for us. He was one of the first Indians, and as a statistician. The reason for statistics is Maulanavis.
I'm sorry, Huzur Bazar was an algebraist, so maybe...
Yeah, but anyway, he in the Department of Statistics, we were all thrilled that an Indian has been able to achieve
What award are you talking about?
I'm talking about... I forget, this old age is difficult to remember the award, but it was a famous award and it was published in the US. And we were anyway, what I wanted to talk about is Donald Glaser. He won the award for Cloud Chamber. And he came to India and he talked about that he's a Nobel laureate in physics, but he wanted to start biochemistry. And this desire for learning, which is related to what avid learning is doing, that learning can be a lifelong process. Absolutely. Can you imagine a Nobel laureate starting off in biochemistry? I attended his lecture at the Institute of Science, and that has always remained with me. Yeah, so the question is, how is it possible for the human mind to change tracks and start in a totally new, different idea, in a totally different field?
Well, I think what happens is, I think that's the thing. We all have these different capabilities that don't get really necessarily exploited the full way or developed. But we all have it in ourselves. And so it's a question of interest, motivation, and a host of other things. And so, that's like when I started, when I started writing, I was not a good writer, and it took me many years to really practice it, and I really felt like, okay, I have something to say. But it took me, I started writing really seriously in 1983, and my book was only published in 2001. I didn't have anything published before that. So, you just have to spend time, and you can develop skills that you might not even know that we have.
Who else? Yes.
So what do you mean when you say fractals don't have an area? I didn't understand that.
Okay, I think you'll have to look it up, because that's hard to...
it's hard to...
Just a brief answer.
Do you want to answer that?
Well, I'll tell you, I was telling you about that, the triangles that turn into a Star of David and on and on and on. So, this is not quite the no area, but it's a finite area that I'm talking about. If you draw a circle around that circle has a definite area, obviously. As you do this, as you keep increasing the circumference, as you keep drawing those little triangles, you're never going to go outside that circle. So, therefore, the area is finite, but the circumference becomes infinite. So that's that kind of fractal. Now, the Sierpinski triangles that he's talking about is a different kind of fractal and has different properties. So, but it gives you the idea. It gives you. Well, the point is that there is a certain kind of infinity, and that gives you properties that you don't expect. And one of them is that there is, in this case, you can think of it as not having an area. Okay.
Yeah, I got a question here.
Who's
yeah. Sorry. Yeah.
Go ahead. Yeah.
You talked about examples in nature of fractals, whether it's the cauliflower, the sunflower, the conch. At a universe level, do you see some kind of pattern in the arrangement of galaxies, or at the pace that the universe is expanding at the speed of light? I mean, is there something that you feel there's a pattern that is visible there, or is that a little bit?
From what I understand, there is a fractal pattern to galaxies and so on. Now you have to remember that the fractals in nature are not the same as fractals that you get out of a mathematical rule. Like if you look at this shell, notice that it's not really self-symmetric in the same way. Parts of it, if you blow up, they'll look a little different. So they are not exactly from a mathematical rule. What they are fractals in a statistical sense. So if you compared this with something that was non-fractal, mathematicians can actually quantify how close it is to a fractal by doing some statistics and saying, if it weren't a fractal, this would happen. But since this is happening, these parameters are like this. So in that sense, it's a fractal. So in that sense, you can find various fractal patterns, but statistically speaking, in a lot of things, including the formation of galaxies and so on.
You're a maths teacher, and you obviously enjoy your subject. My question was that why is there so little enjoyment in the teaching of maths in India here? There's a kind of a dogged concentration on the method.
I hope you're not clapping for more of that. Okay. Yes, right. Yeah, so that's always an issue. How do you make mathematics interesting? And it's not an easy thing. It's very. I mean, I've been teaching mathematics since 1983. So that's like 32 years. And I think for me as well, like the first several years, it was very difficult to make it interesting. And it's only, I think what helped was writing a book, writing novels. And that made me like really look at it from the point of view of people who are in the audience. I think we don't put enough emphasis on some of these things that are considered, like puzzles and so on. Oh, those are just for enjoyment. So I think that's a big thing. I think visuals can help a lot, and that's the more I think that's going to increase hopefully. But I think there's also something to be said about the fact that whether it's for good or not, there is something about mathematics that has to be done by oneself. That you actually have to have that effort that has to be put in. It's like yoga or something, you have to meditate, you have to put in that effort, and only after you have observed yourself and made it your own, only then do you get to see the enjoyment. So there are certain types of mathematics, like puzzles, you can enjoy. Like this stuff that I show you, that you can enjoy. But the true enjoyment that you were talking about, the beauty and elegance, you really have to make an effort. And it's only after you reach that stage that it opens up. So the question is how to take you to that stage. And we have these ingrained ways of teaching mathematics that have just come down for a long time. Now in the US, they are doing this, what is called this Common Core. And they're really trying to redo mathematics and so on. They're putting a lot of emphasis on process. Like when we multiply 3 times 6, what are we really doing? Well, what we are doing is we are adding 6 and 6 and 6. So they're trying to do these, make people understand it. But unfortunately, the gap that's happened there is that the teachers are still using the same types of methods as before. So they're still asking people to memorize, and so it's a mess because it hasn't really progressed in the same way. So teaching people how to teach mathematics is very hard too. So yeah, it's a big problem.
How about you? There, can you give her the mic? Just for your hand up first.
Dilip, that gentleman
All right.
Oh, he had the mic, so maybe.
Let him ask the next question. No, go ahead. Oh, it doesn't work? Will you give him the mic, please?
Yeah.
Okay, take the mic from him.
Can you give us some examples about some infinity pools being bigger than other infinity pools that you talked about?
Oh, well, the example is, the main example is if you look at, you need to know what irrational numbers are. Right. Okay, so here's the best example. If you draw a straight line and you mark a point 0 at one point, and then every 1 centimeter or something you start marking 1, 2, 3, 4, 5. And let's say your line was infinite. And you marked off all the whole numbers. You also went in the negative direction, let's say, -1, so on. You can actually represent each point by a number. Each point will correspond to some number. You'll have 1/2, 1/3, 1/4, 2/3, and all that. Let's just look at the numbers between 0 and 1. So here's 0, here's 1. In between, what are the numbers? 1/2, 1/3, 1/4. But then there are also numbers that are irrational numbers, like, for example, the square root of 2 minus 1 or something like that. So they are irrational.
1 over pi.
1 over pi. These are numbers that cannot be written as a fraction. A rational number can always be written as a fraction, 3/4, 5/6. Irrational numbers, you cannot write them that way. There's another difference. A rational number always has a decimal expansion that at some point starts repeating. So like 1/3 is 0.333333. Something else will be 0.14141414. An irrational number is something that doesn't have a repeating decimal. Like pi, as you said, is 3.14159, blah, blah, blah. Some people can memorize it. So now if you look at the numbers, all the numbers between 0 and 1, that is an higher infinity than the set of all numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's an example. All the numbers between 0 and 1, because you are including these numbers that have non-repeating decimal expansions. So.
Yeah. Hi, Manil and
Hi.
Dilip. I think one of the most fascinating things, since we're having this whole talk on, the intersection of mathematics and humanities, is how no question as of now has been asked on the humanities.
I know.
And for the last 15, 20 minutes, we've been on and on. And one of the, this is something Yes. So I attended this talk by Vikram Chandra, who's also a programmer turned novelist,
Yes.
somebody who's dabbled in the science and maths and moved to the literary world. And he's been doing some very interesting research on geometric patterns in Sanskrit poetry. And I think one of the key things that's missing today is there is this obvious demarcation between the humanities and the sciences, which is changing, but not maybe too soon. And what can be done to have more books which sort of intersect the two? I remember reading this book by Malba Tahan, which is a very interesting sort of Arabian Nights rhapsody on mathematical journeys and stories and homilies, and which explains complex mathematical concepts in a simplified way. But I don't really see a lot of people of the humanities being comfortable enough to write mathematics, and a lot of mathematics sort of condescending, down to the whole level of seeing patterns in literature. The question is, what do you do to make people comfortable to bring mathematics into humanities and talk about sciences in a way which is interesting to the average man? Yes.
Well, first of all, if you want more books on them, buy more books. Buy a lot of books. When you see, buy a lot of Vikram Chandra's books, and other publishers will see that, and they'll want to invite other people to write that. So that's certainly one obvious thing. But beyond that, I think what as you said, these things are happening slowly, and like this play was a reaction to that. There's something called STEAM. Has anyone heard of STEAM? STEAM. So first of all, yeah. So STEM stands for science, technology, engineering, and mathematics. STEAM stands for science, technology, engineering, arts, and mathematics. And the whole idea is that if you introduce arts into the mix, you can actually convey some of these scientific and mathematical ideas much easier. You can kind of lubricate things, and people will actually be much more amenable to absorbing this message. So that's something that has gained steam. That bad pun, so excuse me for that. But that's the thing that you really see. There's big conferences on this and so on. So I expect that some of these things will be coming through at some point. Now, on the other side, the humanities, there's also a push in that. There's a whole field called digital humanities, which is more computer related, like putting humanities out there so that people can actually see what it does and why it's useful. There's a lot of people, again, this is more at the research level in universities, who are introducing mathematical ideas into humanities. Like I've seen a book on like looking at how religions spread, again, in a mathematical sense. There's a lot of work on looking at patterns, like you were talking about, in literature. So I think this is happening more and more. So I'm optimistic that things will improve.
Anyone else? Let's have somebody from here. You've got the mic.
Manil, mathematicians are not necessarily the most flamboyant people. But what do filmmakers and the public, why are they intrigued? There's a movie on John Nash. There's one on Alan Turing. There's one on Srinivas Ramanujan. Somebody was telling me there's one on Johnny Van Neumann. So what is about, and there's not so much really on scientists.
Insanity, which he was talking about.
I mean, all these mathematicians had bad endings. That's the tragic endings. So Ramanujan and Turing and John Nash, he got better. But so that's one of the things that's always fascinating. Mathematics and madness. But of course, there have been things that have treated this seriously. One of them is this TV show in the U.S. I don't know if you get it here, called Numbers, and that's about this team that uses mathematics to solve crimes, and that was a very popular show. So again, people, once Hollywood gets into the act, they can only think one way. My kind of saying on this is that who was it who said if there's a gun in the third act of a play, it has to go off. Yeah. There's a famous quote like that. So if there's a mathematician in Chekhov. If there's a mathematician in the movie, he has to go mad. So that's
But there was also this movie Moneyball, which was about Brad Pitt with about mathematics in baseball, and many games have been analyzed like that. Basketball, I'm sure cricket is amenable. So maybe there are movies there to somebody to do something with that kind of mathematics. Yes, sir.
My question is at the intersection of humanities and mathematics.
Okay.
You would have seen many colleagues, students who are able to write from left to right literature and right to left like Hebrew or Arabic. Have you seen a greater facility for mathematics amongst such so-called ambivalent writers?
Ambivalent? Ambidextrous? Ambivalent, who can go both ways?
So I write English and I write Urdu both with a good facility. Am I known to be better in mathematics?
Well, maybe you should answer that.
I don't write Urdu as well.
Yeah, I don't know the answer to that. I don't know if anyone has done a study. It's an interesting question, and I'll say that there's a broader question there, where neuropsychology, that's a big field, and people are finding all these things in chemicals that are occurring in your brains and patterns and so on, where they're able to explain how people behave and learning abilities and so on. So, the answer to that might be out there, or it might be something that people will look at.
Yeah. Can you hold the mic like that? Yeah.
It's not on.
Like we discussed, mathematics is everywhere. We are analyzing it all over the universe. So, did we actually discover it, or we invented it?
That's like the chicken and egg question. So I like to say we disvented it, discovered and invented it. So that's my answer.
Yeah, quite an ambiguous question.
Or ambivalent.
The thing is that for most mathematicians, I've heard that question, and there's even a book on this subject, and there are different theories.
I asked all my maths teachers this question.
Yeah, but the thing is that as a mathematician, I don't find that question as intriguing or as compelling as the actual mathematics. So in some sense, it's fine to say that you discovered it or you invented it. That's my next project. I'm writing a book called The Godfather of Numbers, and that's going to look at this idea much more closely. So
you have Marlon Brando playing the lead?
No, he's dead. So
Okay, let's have.
We'll just take the last question.
Last question. Okay.
Yeah.
I am really interested in poetry, so could you suggest some poems that have been, like she said, that we haven't really talked about poetry, so that have, used mathematical concepts, like Kabir was writing about Shunya, right? So, could you give more examples, because I'm...
Yeah, so there's a whole branch, there was a whole movement called Oulipo, O-U-L-I-P-O, that they actually use a lot of mathematical rules to create poetry. And their idea is that if you constrain yourself in some way, then that'll unleash your creativity. So if you look up on the web, O-U-L-I-P-O, that's a good place to start. Some of the poems that...
that's in your play too, right?
Yeah, that's in my play. So, and then there's some actual poems that if you go to my website, we actually have the whole syllabus of the class that we did, and that has several poems in it that actually, there's one, I don't know if I'll be able to remember the name, but there's one about infinity. One is...
Not that Edna Vincent.
That's another one by Edna Vincent Millay, and that talks about Euclid. Euclid alone has looked at beauty bare. So, she has some mathematical themes in there. So that's another one you could look at.
There's a lovely poem in Marathi on the root of -1 by Nanda Karandikar. Maybe you should read it.
Yeah, that sounds good.
-1, Hey Omkara.
Do you want last question?
May I go?
Yeah, definitely.
May I ask?
It's sorry. Go ahead.
About this,
sorry.
What you asked about poems and constraining, you have sonnets which have...
Exactly, that was my...
Yeah,
so...
that constraining itself can produce poetry.
So I remember reading Vikram Seth, and every page I would Golden Gate and actually counting it syllable for syllabus to make sure he stuck to his iambic pentameter. But so the thing is, my question is there a quantifiable tendency towards good poetry? Can you quantify it mathematically in any way? Is there a rhythmic consonance to it, or is there something on those lines, or popular music as well?
Well, you're asking a very difficult question. I think what you're trying to say is that can you quantify aesthetics?
Yes.
You can certainly quantify all these rules, like you mentioned, the sonnet, and as you counted and so on. But you're asking to quantify taste in some way. You're saying what is good poetry and what is bad poetry, and can I make a mathematical judgment of that? And that's a difficult question in general for any kind of art, right? How do you quantify aesthetics as a numerical value? Because it's so personal, it's so subjective. Now you could do it in terms of if people said, okay, we are going to make a set of rules, this qualifies as good poetry, this qualifies as bad poetry. You can quantify things like how popular a song is going to be. You can quantify popularity. Like a lot of these, when you go into some of these programs that will tell you which song you will like, that what they're doing is they're looking at various aspects of a song, like they're counting the number of beats and they're counting this and they're doing that. They're making a big table and they're actually getting a number, assigning a long string of numbers to that song, and they're comparing it with other songs that match those that are close by. So there are things like that people are doing, but this is an active research area. And so aesthetics by themselves, they're much harder.
Thank you, Manil, Dilip, and Dilnaz for a very entertaining evening. We also like to thank Anamika and the team at the US Consulate once again for their support in making tonight possible. And last but not the least, thank you all for being here. Please do join us again for our upcoming programs, a masterclass in documentary photography with Fauzan Hussain the following Saturday, a workshop on writing children's fiction with Anushka Ravi Shankar, and a kaleidoscope of literature masterclasses at the upcoming Kalagoda Festival 2016. Thank you.